Hi everyone, so today we're going to look at the concept of a circuit. Now you should have already gone through chapter 1 in the textbook as well as the first set of slides, which covers things that you should already know from high school, like voltage, current and power, what they are, how we derive them, how we represent them in a circuit, voltage sources, current sources, and the basic components and their representations, that is resistors, capacitors and inductors. So today we're going to look at how we bring all of these things together in order to make a circuit. And we look at some basic things like open circuits and short circuits, and then some of the basic components of the circuits. And most importantly, we're going to look at the concept of nodes, which is quite simple, but it often gives beginners a bit of trouble because it is a bit abstract from a physical circuit. So to get into it, what is a circuit? Now if you think of a circuit of any kind, like a racing circuit or even the circuit at the gym, it refers to a closed pathway. You start at one point and you go through something and you get back to the start. And it's the same thing with an electric circuit. In this case you're talking about current, and the current is going through some conductors and some components, resistors, capacitors, inductors, etc., and it is going to eventually come back to the source. So this is basically what we mean when we talk about a circuit. And you could see here from the diagram, this is the source, which is a battery, and the current will start off coming from the positive terminal, go through the resistor, and eventually it goes back into the negative terminal of the battery. Now very importantly, we should note here that the voltage arrow across the resistor here points in the opposite direction to the current. So that is always true for passive components. As long as you specify your voltage in one direction, the current should be in the opposite direction, or vice versa. You specify the current in one direction and the voltage should be in the opposite direction. And this is only true for passive components. For active components such as sources, like this voltage source here, we will see that the voltage source, the arrow which tells us which direction is positive, this is positive here and this is negative, so the arrow points to the positive terminal. We see that the current is actually in the same direction as the arrow. This is not always true for sources. It could be in either direction. So this is something that is very important to remember. So some special types of circuits. We have an open circuit, which is really a point of discontinuity in the circuit. No current could flow through it, so it is essentially a break in the circuit, and it means that there is an area where there's infinite impedance in the path, so that no current could flow. And the other one is the short circuit, and the short circuit is where we have zero voltage between the nodes. So if we look at the open circuit going back, between these 2 points we have no current flowing for the open circuit, whereas for the short circuit, between these 2 points we have no voltage, 0 volts. It's essentially the same point. And we represent the short circuit by just simply connecting the 2 nodes together. Now when we talk about these connecting lines, one of the mistakes that people make is often that they think these connecting lines represent physical wires. So you have an electrical cord, the plug coming from your laptop, anything like that, and you think that these wires, when you draw the wires in your diagram, and we think that these wires here, these connecting lines, are the same as those wires. They're not. They do not represent physical wires at all. They just tell us what is connected to what. And if we actually look at, say, a power system, and we have all these transmission lines going in the power system, which are essentially just thick wires, we don't represent it with a line. What we actually represent these with are a combination of inductances, capacitances, and also resistances. Here we don't have the resistances put in, but the resistances are also there. So the connecting lines do not represent wires. They just tell us what is connected to what. So that is a very important thing to remember, and it will come in when we talk about the concept of nodes later on. Now, if you look at this circuit that I have drawn right here, one of the chief aims in this course will be to figure out what are the different voltages and currents in circuits. In a circuit, well, not this simple, it's going to get a lot more complicated than this, but what are the voltages and currents throughout the circuit? Now, if I ask you for this simple circuit, what is the voltage, say at this point here, you might be tempted to say it is V volts. And that would be wrong. Why is it wrong? Because we do not have a reference point in the system. So we know that V volts is across this device, but we don't know what the voltage on this side of the device is. So we can't say that this is definitively V volts. So in order to give a specific number to any voltage in the circuit, we have to come up with some sort of reference point. And this is where you hear things like ground, earth, and neutral. Now when we talk about ground or earth, it is the potential of the actual ground or earth, the earth that you stand on. And we designate this to be 0 volts. And this is a reference point for measurements, especially in the power system. So if you go to a substation, say, you will see that the measurements are taken from the transmission line or from the bus to the actual earth, the ground. So that is for a power system. Now, there are many devices where you don't actually connect to the ground, like your cell phones, your laptops, basically anything that works with a battery. You don't have a ground, but you still need a reference point in the circuit so that you could calculate all your other voltages. So everything is with respect to that point, and that is what a neutral is. In some circuits, like the power system, the neutral is often grounded, but as long as you have something floating like an electronic device or so, the neutral is actually not at ground potential. For that device itself, we may designate it to be 0 volts, but that does not mean that it is the same 0 volts that is the potential of the earth. Now, the symbol for earth or neutral is actually the same, and we see them here. These are the two typical symbols, and when we put them in to the diagram, you can see it in two ways. Sometimes we see it like the one depicted in diagram A, where you have the full circuit connected, and then we have the ground connected to one particular part, and that tells us what the potential is there. So in this case here, since the ground is connected here, I could say here is 0 volts, since that is the potential of ground. And now I know that I have X volts across this source, so I could say that this is X volts DC here. Now this is exactly the same as diagram B, although diagram B does not have a direct connection from this side to this side. An earth symbol is not the same as a resistor symbol. So I could have a circuit, for example, with 2 or 3 resistors, R1, R2, R3. I could have a circuit like that, and these components all represent different physical components. But if I have different grounds, they all represent the same thing. It is the same component. All we're looking at here is a way to easily represent, really a way to remove the lines in the system, to make the system a little less dense. So you can imagine this is a very simple drawing. If you have a diagram with hundreds and hundreds of components and a lot of connections coming back to ground, it is going to get very, 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 very messy. So instead of drawing in all the lines, we just put these ground symbols at different points so we could clean up the diagram, and that is essentially what ground is. Now we could do this because these grounds represent the same nodes, and this is the last thing we'll talk about for this session, and that is what is the concept of a node. And a node is an area of common potential that is bounded by a set of circuit components. Usually when we think of nodes, we think of points of intersection, we think of single points, not really whole areas. And that is still true as long as we remember that the lines, the connecting lines in our circuit diagram does not represent physical wire. So if we see something like this in a circuit diagram, and we have a component here, a component here, a component here, and a component going up here, it is not that this is one node and this is one node. All this tells us is that all of these things are connected together, so that this is connected to this, is connected to this, is connected to this. That is all it tells us. So let's see if we could identify some nodes in a circuit. So we're going to identify the nodes now. How do we do it? We simply start at any point of the circuit. So I'm going to start at the source here, and I'm going to trace the connecting line, and wherever I reach a component, I'm going to stop. So that's one node. Then I cross the component and I come to the other side. That's two nodes. And then the last one will be here. Three nodes. So the other one, diagram B, again we come this way. Now we branch out, but both branches are captured in the node, and the same thing on this side. So I have 1, 2, 3 nodes in this circuit and 1, 2 nodes in this circuit. Now you could pause the video and see if you could identify the nodes in these two circuits. Good. So if you've done that now, what you should have is for circuit A, you could get this one. Now if I cross over to this side, I will get here, and if I trace the wire down, I will get that. And we see that in each one of these nodes there are no components. So the node cannot contain any components, because as long as you go across a component, you're going to drop in voltage, and the node is an area of common potential. It is physically the same point in a physical circuit, but on the diagram, because these just tell us what is connected to what, it could be distributed across the diagram. And for B, if we do it, so that is what you should have. And that brings us to the end of this session. So just to summarize, we looked at what is the concept of a circuit. We looked at open and short circuits, connecting lines, and the representation of ground and neutral, and very importantly, the concept of nodes. Next time we will look at how do we actually go about determining voltages and currents. So we look at Ohm's law, Kirchhoff's law, voltage law, and current law.